I'm Michael, and this is Leo, the two-legged walking robot. So in the last update, I showed how he can crouch his legs and do that repeatedly. Surprisingly, there's actually a lot more going on behind the scenes than just bending right here, and bending right here in order to bend the legs. I mean, his legs are really complicated, but that's actually a good thing in a weird way. So let me explain. So for simplicity on my end, and to make sure that his feet are always level with the floor, Leo's legs are built off of parallelograms. So there's one parallelogram for the top section and one for the bottom section. And these parallelograms are able to bend forward and backwards by use of the two actuators inside of the legs. Actuators are just motors that move in a linear motion rather than rotational. So before I can actually explain how it is that the code works and all the equations that I wrote, first you're going to have to understand how Leo's legs are actually built. So I've got two things here. One of these is from the side view, and one of these is from the front view. So on this one, from the side view, this is his legs when they're standing straight upwards, and this is it when they're bent. So like I said, they're built off of parallelograms, so no matter what happens, these two will always be parallel to each other, and these two will also be parallel to each other. So the distance may be shorter, but his foot will always be flat on the ground in this axis. So in order to bend these, all I have to do is get these two corners to go further apart from one another. And then since these are all on joints, when something in the middle extends, it will bend his leg. And then vice versa over here, when this thing in the middle extends, it will bend his leg. And if it retracts or is in the neutral position, it will make his leg straight. So technically his leg can bend backwards if you were to pull the actuator in even further. So that's how that works. But if this was it, then you'd only have to have one actuator in each section of the leg, because it's only bending the leg. But we have two actuators in each section of his leg. That's where this axis comes into place. So not only do we have joints here, we also have a joint at the top of the leg and at the bottom. And this allows his leg to bend outwards like this. So the way that this works is we have two actuators which are connected at the base section of each section of the leg, and then they go out and connect to the bar up here. They don't connect to the top section of the leg, they connect to all the way up here above where the leg is connected. That means that if we do the same thing over here, this actuator is going to be longer than this actuator, because this one has a further distance to go in order to push the whole leg out. So if both actuators are always the same length, then his leg will always be in this upright position, and when I push and pull both actuators, it will simply bend the leg, as you see over here. But if I were to push one actuator forward and one backwards, it would keep the leg at its position that it is in this way, but it would bend the leg this way. In the code, when I'm telling Leo how to bend his legs, if I want it to go like this, then I add the two values of the actuators together. If I want it to go like this, I subtract one value of an actuator to another value, and that gets me to two motor speeds. So the way I actually tell Leo how to position each section of his leg is using something called a PID controller. That's literally just a PID controller. And PID stands for Proportional Integral Derivative Controller. So that is a lot of weird words and long words, but what they mean is basically I give Leo a demand position where I want him to be at, and then he will try his best to get those actuators to the position that I told him to go to. So if, let's say this is a graph of where this is over time, and then this is his position. So we're going to create a line here. Let's say that's where I want his leg to be. And let's say his leg starts out at the exact same position. Well then, as time goes along, the demand position that I showed before doesn't change. So his actuators aren't going to do anything. They're just going to stay off, not even turn on, and they're just going to stay at the exact same spot that they're at. That's perfect. But what if this happens? So Remember, black is the demand position, so currently he starts out where I want him to be, right? He starts out at 0, and he's going along, and he's like, okay, yeah, I'm good. I don't even need to turn my actuators on. I'm in the correct position. And all of a sudden, whoa, I'm not in the correct position anymore. What do I do? So Leo has to figure out how to get to this new position that I told him to get to, and that's where PID comes in. This is used in thermostats and that sort of thing because you set a demand temperature that you want your house to be at, and then the thermostat will automatically turn on and off the air conditioning or the furnace to keep your temperature at the temperature that you told it to be at. This is the exact same way, except for instead of temperature, it's using positions. So I tell it to be at this position, and he is already at that position. He doesn't need to do anything. But all of a sudden, I change it. Like, I set the temperature in my house to 30 degrees instead of 70 degrees. And all of a sudden, the thermostat goes, whoa, I'm not at the correct temperature anymore. I need to start changing some stuff. And that's what Leo's doing here. I give him a new position, and he's like, whoa, I'm not in the right spot anymore. I need to start changing how I act. So he needs to get up here. How does he do that? Does he just say, okay, all the actuators turn on right away, let's just go full speed? He would probably go like that. That would not work. And if he turned on all of his actuators, then it probably wouldn't even move him in the correct direction. So that just doesn't work overall. The way that he figures out how he needs to move to is using an equation that I actually derived myself, which best gets his leg to the position it needs to go to. So I just created another graph down here, which is still over time, and this axis is position, and this axis is time. So this is the demand position. So when I turn on Leo, he already is in the incorrect position. So right away he needs to change that. So Leo does a little bit of math, and he figures out which direction he needs to turn on each actuator in order to get to the new position I tell him to. So if he just went full speed right away, then he would start out like this because he's still computing what he's doing, and then he's like, okay, I gotta turn on full speed. Then his position would go like this, and then he's like, yay, I got to my position, I'll turn off my actuators. But because motors have inertia, motors want to keep moving. They don't just stop on their own. His actuator is going to move a little bit further without him wanting to. And then it's going to end up around about here. And then Leo's like, wait a second, I'm still not at the position I want to be at. I need to turn the actuators the opposite way I just turned them in order to get him back to my position I want to be. So he turns his motors on full speed, and he starts going down, and he gets to the new position, he turns off the actuators. But like before, his actuators are going to keep moving because of inertia and momentum. They want to keep on moving. They're not just going to stop by themselves. So they keep on moving further. And they get down to here. And then Leo's like, wait a second, it's not in the correct position. So he keeps on doing this same thing over and over again, and he never actually gets to the position he wants him to be at. So this is why if I set his actuators to full speed, and there's no variables in there, just either on full speed or off 0, not moving, we would get a graph like this, which just does not work, and he would never be able to get to the position I want him to go to, and his legs would just start oscillating back and forth because he's not in the correct position. So that's where my equation comes in. So this is a graph that I made which shows the distance of where Leo is compared to where I want him to be, and the speed of the actuators. So if he is at 0 distance, and he is where he's supposed to be, then I want his speed to be at 0, like that. But if he's at as far a distance as he could be, then I want his speed to be all the way at its full value, at 100%. And speed, just because of the way Arduinos work, speed is from 0 to 255, so this is basically just 100% speed. So 255 means 100%. So if it's at 100%, if it's at 100 distance, I want it to be at 100% speed. If it's at 0 distance, I want it to be at 0 speed. So this should be simple, right? Boom. There you go. I got an equation, y equals x. Done. Okay, first off, that doesn't even work because if I did y equals x, it would go up and over 1, and then up and over 1, and up and over 1. But that's not even what I want because it's 100 and 255, so I'd have to do x divided by 100 and then times 255 to make this equation work. But still, it's not quite right, because this makes it so that his actuators are only on full speed if it's at the maximum distance that he could be. I mean, this technically does work, but I want him to be better than that because I don't want him to be slow. I don't want him to slow down so much as he gets close to where he's supposed to be. So that's where I created my own new equation. So once again, this is a 255, and this is 100, and this is still speed, and this is still distance. What I did this time is created a graph that looks like this. So this is an interesting shaped graph, but what this means is that if he's at 100 distance, then he'll go full speed, but even if he's not at 100 distance, if he's somewhere around here, he'll still be going full speed because I want him to go as fast as he can to get to the new position that I tell him to. But then starting here, all the way down to here, he's going to be slowing down. But he's not going to be slowing down linearly. He's going to be slowing down exponentially. So as he's going along, he's going to start slowing down a lot and a lot and a lot, and then he's going to kind of smooth out and then only slow down a little bit at a time until he gets to here, and then eventually it'll just curve down and go back all the way down to 0. So some of you may be wondering, why did I not make a graph that just looks like this? Well, first of all, I want that top speed at the top, like I explained. But also, why did I not go down to the very bottom of the graph? Why did I go here and then down? That's because if his motor speed is from 0 to 255, right? So if I were to give him a motor speed of 10 out of 255, that's not very much. And literally, it's not even enough to make the actuator move. Because this speed variable that I'm talking about isn't the actual speed of the actuator, it's just how much voltage I'm giving it out of the max voltage, which is 24 volts. So if I were to give him this much, let's say that's, I don't know, 5 volts. This would be 5 volts down here. That is barely enough for his actuators to actually move. Down here, below this 5-ish volts line, it's not going to actually move. So what this graph is more like is like this, because it just drops off, and that's not good. So that's why this graph is shaped like this. So using everything that I learned about PID and these motor speeds and the distance and these exponential equations, this is what I have for an equation. Y equals x minus 10 divided by 95 times 245 plus 10. So this will give me a graph that looks like that. So that doesn't actually work because that's going way too high of what I want it to be, right? So in the math, after I figure out the speed, so let's say the distance is right here, that means that my speed is going to be way up here. That's way higher than 255, which is down here. So right after, in the code, right after I calculate the equation, then I just constrain it so that it has to be within this line. So if it's above 255, then it will just bring it down to where it has to be. So that, in a sense, creates this line right here. And that's about it.